Okay, so our first presenter is Aurelio. I hope everybody can hear me over the Zoom, right? So our first presenter is Aurelio Negri. So Aurelio is third year student in computer science department, and he is going to present Pythia, a customizable hardware prefetching framework using online reinforcement learning. So this work was presented last month in Micro 2021. So Aurelio, yeah, stage is yours. Thanks.
Okay, thank you. Can you hear me right? It's working fine?
Yeah.
Okay, perfect. So welcome to my presentation. I'm gonna dive right into it. So we're gonna start first with the executive summary. Small background first. We're gonna say what is prefetching. So prefetching is a method used for predicting future memory accesses, and it's gonna be based on past patterns of memory accesses and also other features. Then what are the current problems with the prefetchers? So the current prefetchers usually rely on only one feature. They don't have any system awareness. They have a lack of customizability. And then also with machine learning approaches, there is usually a large memory overhead. So the goal of this paper will be then to use multiple features for learning and prediction, and then also have some kind of system level awareness and the possibility to be having a customization in silicon. So then the contribution will be an online approach, as I said, customizable, and also practical approach as well to the problem. So the key results, this prefetcher was evaluated over different workloads, and the current state-of-the-art prefetcher were outperformed by from 3 to 17%. So then quickly the outline of the presentation. So we are gonna have the introduction. I will explain what prefetching is, the limitations that we are having with the current prefetchers, what will be the goals, then how does Pythia work actually, or how is it implemented, and we are gonna show the results in comparison more in detail, and also what I think are the strengths and weaknesses, and then we are gonna end with the discussion. So what is prefetching? So as I explained before, we have the problem in computer architecture that when we are trying to access the memory, the main memory, it's usually a really long latency problem where it takes a lot of time, and so the CPU usually has to wait. So what the prefetcher tries to do is try to kind of predict what will be the future memory accesses, and this prediction is usually based on memory access patterns or also some other program features. That program features might be like the program counter or the page number. And then to kind of describe how a prefetcher performs, we use 3 metrics. One is coverage. So coverage is kind of how many cache misses that we can avoid using the prefetcher. Then the accuracy measured actually how many prefetchers that we are actually doing will end up being actually needed by the CPU. And timeliness is how much before the actual request by the CPU do we have to do the prediction, so that when we have done the prediction, it's already in the cache once the CPU needs it. So what are the problems then with the current prefetchers? So the paper compares this Pythia to mostly 3 of these state-of-the-art prefetchers, which are SPP, Bingo, and MLOP. And there are actually 5 fundamental problems that we are trying to improve. So the first one, as I explained before, is single feature prediction. So almost all of the prefetchers rely on only one feature. Then the lack of system awareness. Usually by system awareness, we mean especially like the memory bandwidth. So they usually don't change their behavior if there is a high bandwidth. Then we have the problem with the design customization. Usually, maybe we want to customize our prefetcher based on the workload it's working on, but it's not possible with the older versions, the other prefetchers. Then compared to other machine learning approaches, we want to have a small model size, which is usually not the case for the other machine learning approaches, and also low latency, which is also a problem with the other machine learning. So what are then the goals? So we want to use multiple program features, then we want the prefetcher to be able to adapt his behavior. Also, when there is a lot of bandwidth being used, then we want to be able to be customizable and also kind of easily customizable, so that we see, like, if you change these parameters, it's going to have this effect, right? And also we want to be able to decide which feature we want to use, because maybe there are other features that might be useful in some situations, or in other situations we can use different features, right? And then in the end, since this is going to be, I will show you later, this is going to be a machine learning approach, and we want to have also a small memory overhead and also a small latency, a low latency. So I will explain first the basics of reinforcement learning, because Pythia is based on this machine learning approach. So as you can see, there is environment, which in our case will be like the system, that is going to provide a state. Usually the state is going to be the features and maybe the bandwidth. And this state is going to be provided to the agent, which in our case is the prefetcher, aka Pythia. So then based on that state, the Pythia is going to take an action at time t. And then based on that action, let's see if it was a good decision, it was a good action that it decided to take, then there's going to be a good reward. Or in the other case, a bad reward. So based on the action that it was taken, it's going to be rewarded accordingly. So in a bit more detail, so what is the prefetcher is doing, or the agent is doing, is follow this policy that maximize the cumulative reward. So long term, we want to, with some of all the rewards, we want to have the maximized reward at the end. And how do we measure it? How do we know? So basically, we have this expected reward that we associate to a state and action pair. So for that status, for that action, our agent expects to have that reward, right? And for updating this expected reward, this function, we use this stars algorithm, which is pretty common to be used inside the reinforcement learning. And you can have a look. It's based also on the next. So because we also care about the long term, so you can also see that inside here we also have the next step, the next time step, and then we also have 3 parameters to kind of decide and customize it a little bit. So the first parameter is alpha, which is here. It's going to be our learning rate. And alpha is a bit like maybe you've seen in machine learning. It's kind of like, the learning rate. So if it's big, the alpha is big, then it might be that it's really fast to converge, but then we might overshoot the solution. So we have to kind of tune in it a bit. Then gamma is going to be the discount rate. So the discount rate, you can see, is right next to the next time step. And it's kind of like a measure of how much do we care about the long term versus the short term rewards that we want to have from the algorithm. And then the last one is the exploration rate. So there might be the problem when we are starting to run this algorithm that we always focus on the same action that might happen. So to avoid this problem, what we are doing is that with probability epsilon, we take a random action so that we kind of explore also other solutions that might be better, but that were not explored previously by the agent. And so how do we implement it? So we define the state is going to be a k-dimensional vector, which has 2 components from program features. One is a control flow, and the other one is data flow component. Then the action is defined as the prefetch offset. Usually the prefetch offset is going to be from the current request that the program made, from the CPU made, for example. And then we are going to have, for the reward part, we're going to have 5 different types of reward. So the first 2 rewards are kind of similar. So accurate, it means that our prediction was accurate. It means it was needed by the CPU afterwards. And it was also timely in the first case. It means that when the CPU requested it, it was actually already in the cache. Or late, it means that it was requested, but it still was not already in the cache. Then we have loss of coverage, and this happens when the offset points to another page in the main memory, which is not going to be very useful to us. So this is a kind of a negative reward. Then we are going to have the inaccurate one, which is actually the opposite. We are doing a wrong prediction. And the no prefetch is just here we decide, okay, we are not sure what we are going to do. So let's just decide, okay, we are not going to do any prefetch. So here you can see low or high. As I said before, because Pythia is system level aware. So low harm means specifically for the bandwidth. So we're going to assign a different type of reward based on the current bandwidth of the system. So for example, if you're doing an inaccurate prediction, if it's a high bandwidth situation, then it's going to be even more damaging, right? So if the reward is going to be even smaller. So then on the hardware side, what we're going to have is two structures. The first one is going to be the QValue Store, which will save all this, as I explained before, all these expected rewards for all the state and action pairs. Then we are going to have this evaluation queue, which is a first in, first out queue, which is going to save 5 elements. So it's going to save the action that Pythia took at that time step. Then it's going to save the generated prefetch address in the case we decide to try and get a prefetch. Then it's going to save the reward for that action that we decided to take, the state that was that we had at that time step, and also a field bit. This field bit is going to come handy also later. It's going to kind of tell us if our prediction was timely or was too late. But I will explain a bit better later. And then also we have to remember the initialization. So obviously the initialization, the evaluation queue is going to be empty. And then we are going to set all the values, the Q values inside the store as 1 divided by 1 minus gamma. Okay, so here is the algorithm. So we start with step 1. So at each demand from the memory demand from the CPU, we are going to first check inside the evaluation queue. We are going to see, okay, was this address already prefetched by Pythia? If yes, then we are going to check this field bit, and we are going to see, okay, is this actually already filled inside the cache? And then we can say yes, okay, the reward is going to be accurate and timely, or in the other case, it's going to be late. Then the second step is going to be get actually the state vector that we will need for measuring the expected reward. So we look inside the QValue Store. We have the state, so we need to get the best action for that state. I'm going to explain this a bit better later, how this works. Then the next step is going to be based on what we decide for the action. It might be if you decide to no prefetch or out of page, the offset is out of page, then we can already say, okay, we have also the reward in this case, which is going to be a negative reward. And we can already insert this in the evaluation queue obviously without the address, because we are not generating any address in the end. On the other case, if we decide actually to output an action, so an offset, what we are going to do is generate it, obviously. So we are going to request that address from the main memory. And then also here, we're going to update the evaluation queue. In this case, we're going to update it still with the action that we decided to take, the state that the system was in that moment, and then obviously the address that we generated. Then importantly is also we have to remember to update the evaluation queue, the Q values. So remember that we have the eviction. Here we have the reminder as the reminder here is the algorithm. We evict the last entry. Reminder is a first in, first out. And so we know that when we evict this, the last entry is going to be then t+1. So we also have this information. Then these are all the parameters that are given. And then we have to consider, okay, what is the reward? So in all the other situation, we already have inside the evaluation the reward. Just if it's an inaccurate action, then we need to assign the reward also in this case. And we know because if there is no reward assigned at that moment, then it's going to be an inaccurate prediction, right? And then we are going to use this algorithm. We're going to update the right entry inside the QValue Store. And then every time we see that the cache gets filled, we also go inside the evaluation queue and check where is this data coming from which address. Is this address inside the evaluation queue? Yes or no? If it's yes, then we're going to set the prefetch, the field bit to 1. So we say, okay, we have this in the cache. So here is a bit, if you're curious, the pseudocode for the algorithm, you can also have a look for it on the paper. And so then I'm going to explain a bit better how the QValue Store works. So we have to imagine each feature that we decide to consider for our prefetcher has its own vault. and each vault is divided into different planes. So for this implementation, they use 3, but you can decide how many you want to use. And then what is the plane? A plane essentially is what it will contain then the data. It's going to be the bidimensional array that contain the action versus the feature space. So inside of it, we'll have all the Q values for each action feature, the action space as pair. And then here we have a problem because the feature space, let's say that we are considering maybe the address, right, that we want to request. If this is gonna be considered as a feature, maybe it has 64 bits, right? So it's gonna be a huge array if you consider all the possibilities. For each bit that we are adding is gonna increase exponentially, right? So we are performing some tile encoding with some hash function. And then that's why we also need multiple planes, because each plane is associated to a different hash function. So we are avoiding collisions between the planes. So here we have then a more like graphical point of view. So as you can see here, each program feature has its own vault. Here the action comes in. And then here we can see, okay, we generate the index inside the plane. These are all the planes. So we are gonna do a shift and then the hash function. We're gonna extract the index. Then we are gonna look inside the plane from action states. So here we get the action state Q value for that specific feature. And this happens by, well, when we are summing up also, we have to sum up all the 3 planes, like all the 3 entries. And then finally, we are gonna take, okay, what is the best feature that kind of with that state give us the best state action Q value? So we're gonna take for between all the features, the maximum value, and then this is gonna be considered our final state action Q value. So you have to remember, right, that we have to decide what is the best action. So we cannot just do it once. We have to run it sometimes because we need to consider all the possible actions. So what we are having basically is a pipeline, as you can see here. And at each stage, you have to imagine, okay, there is an action here, action here, action here. So remember, the action is going to be like the offset always. And so I already explained this part. We're going to basically generate the index, look inside the plane, sum up the values between the 3 planes, then take the best feature for that state. And for that action, and then every time here at the end of this last stage, we always keep them. We track the maximum value, so the maximum value for that action. In the end, we are going to have the best action for that state, right? So we are always like updating if we encountered a maximum Q max value. Then another important thing we have to consider is actually all the hyperparameters, right? As you can see, there are a lot of hyperparameters that consider, like how much is the reward, all the hyperparameters for the SARS algorithm, which program features we are actually considering, and also how much, like the prefetch action list. Let's say we have, for example, a 4 kilo. Usually, like in this example, they considered a 4 kilobyte page, and each line in the page has 64 bytes, right? So there are 64 lines, so we have to kind of have a offset between -63 and 63. But of course, not all these offset are gonna be always needed. It's kind of a waste to keep all this offset as in the action list. So there are some important offset that we are going to consider. So let's start first actually with the features. So those are the 2 features that they actually come up with that were the most useful ones. And you can also, if you look at the older or the other prefetchers, they also usually consider either one of the 2 as their features for doing the predictions. Then for the action list, as you can see, they kind of tried and removed some of them and see what was the impact. And they came up with these 16 ones, these 16 offsets that were the most used ones inside when prefetching. And these are the rewards. Also here, they were kind of like fine-tuned. So you can see, for example, this is the reward for an accurate and timely prediction. And it's gonna be 20. Or here, for example, we have inaccurate prediction. For a low memory, like low bandwidth situation, it's gonna be -8, which is a bit bigger than -14 when we are in a high bandwidth situation, right? And then finally, the hyperparameters. So these were found with a grid search. So I don't know if you know exactly how it works, but they were trying like different combination, and they tried 1,000 combination between these 3 parameters, and they came up with these 3 values. So then we are gonna have also here the how much is the overhead and power area and power overhead. So you can see Pythia is roughly for all these chips, they have about 1% of area overhead, a bit more, and the power overhead is less than 1%. So the storage overhead, a bit better explained, is, as you can see, we have 2 volts, as I explained before, 3 planes. Then the feature dimension, we are scaling it down to 128 times 16 actions, as I said before. So each Q value is going to be represented by 16 bits. So the side of the QV store is going to be 24 kilobytes. And then the evaluation queue is going to have 256 entries with all these 5 elements that I also explained before. So in the end, we're going to come up with 25.5 kilobytes, which compared to other prefetchers is actually kind of comparable. Some of them are smaller, but it's not like a huge big difference between other prefetchers, as you can see here. So then I'm gonna explain here the results a bit. So the first situation is gonna be on a single core chip. So we are gonna use, as you see, those 5 are some workloads. You can see almost in all situations, the speed up of Pythia is better than the others, except for this one where Bingo is a bit better. And if you take the average, the mean, then it's gonna outperform the others. And the same when you're considering a 4-core system, the situation is similar. And just in this case, it performs always better. So you can see, we almost for all workloads, we perform better. And we said that we can also customize Pythia. So they also customized specifically for those workloads. And they also here got over the normal Pythia from 2% to 7.8% improvement in speed up. Then another interesting thing is obviously the number of cores. So they tried to increase the number of cores and see what was the speed up. And as you can see, the more you increase the number of cores, the higher the gain is, right? So it always outperforms in all core configuration, but the higher the core count, the more the gain is. So this is actually because, as I said, when there are more cores, the bandwidth is usually larger. So what's going to happen is that Pythia kind of, as I said, is more aware of that situation. So it adapts how it works, adapts its behavior, and it performs better than the others because of that. And here is more, also here, they are fine-tuning the DRAM bandwidth. So this is also always better than the others. So you see, for all bandwidth configuration, it also outperforms the other solution. Okay. So then we are coming up to the strengths. So what are the strengths, in my opinion, for this? For Pythia? So the first one is, as you could see also before, is actually that we can take memory bandwidth into consideration and adapt this behavior based on that. Then we are gonna see also in other like different workloads also there, it can be it's not static. Usually the other prefetchers are more statical. This is dynamically. So we see evaluation queue gets always updated, so it's adapting its behavior on what it has to do. Then I think it's also well optimized for a machine learning approach. It doesn't occupy too much space, and also it's kind of scalable, right? If you want to make it maybe more powerful, then you might increase the size of the QValue store. And then of course we have the possibility that we can customize, but also it's pretty easy to customize. You see, maybe it's really easy to see what are the results if you customize, let's say, the reward. If I decide to maybe increase or decrease how much the reward for the no prefetch has, so it means that we are kind of pushing Pythia to do prefetches all the time. And so it's also pretty understandable what is the result for them. And then obviously this reinforcement learning idea, it's also applicable to other areas in computer architecture. So I find this also really good. Then for the weaknesses side, so the first weakness that I think is pretty considered is that they don't have any latency comparison. So I said that it's gonna be surely better than other machine learning approaches, but they didn't actually do on the paper any specific latency comparison with the current prefetchers. And you have to consider that the slower it is, the timeliness get also affected by this. So if it's slower, then it means it has to do the prediction before, and it's gonna affect like the outcome. Another point that they didn't mention and they didn't explain about, or they didn't try, I'm not sure, is that they didn't try to make it more like a more realistic model to what you would normally implement a reinforcement learning implementation. And they didn't kind of check, okay, if I make it more bigger, for example, QValue Store, well, how much performance am I gonna gain from that, right? Then another problem, and I think this is the biggest problem with Pythia, is that compared to the other prefetchers, it actually needs some training time before it can predict accurately, or it can predict better than the others. So we need to have some, usually they use 50 million to 100 million instructions to do the training before actually testing how it was performing. Okay, so here we're gonna end up with the conclusion again. So if you want to take a screenshot or you want to have a look again, we went through this already. And then we are gonna do the discussion a bit. So the first point is about the discussion is obviously the training time. So how do you think that we can improve the training time on a single core system? And here I'm open to some suggestions from the public. Or I will wait a couple of seconds and then I will also give some input myself.
Yeah, already we have some questions here. Yeah, I'm just
okay.
So thanks for your presentation, but I guess I have a little question before we move on to the discussion.
Yes, ask me.
Yeah, can you maybe explain the first step of how Pythia is implemented? Or more specifically, I don't really understand what reward are we assigning there? Like what are we doing in the first step? Because from my understanding, at that point, we only know the request and nothing else.
You mean in this situation, right? In this algorithm?
Yeah, exactly.
Okay, so the reward basically, yeah, so it's a bit tricky. So for example, the accurate reward, we are gonna assign it inside the evaluation queue, in the queue entry, when we get a request from the CPU, right? So the CPU actually gives a request to the memory, but we also check inside the evaluation queue, maybe this request was already done before by Pythia, right? So we go inside the evaluation queue in this situation, and we check, is this already inside the cache or was this requested before? We see, okay, this matches actually the same request is inside the evaluation queue, means it was already requested before. So we can also insert inside the evaluation queue the reward for that. In this case, the reward might be accurate and timely or not timely, depending on the field bit. For the other, for example, for the other rewards, so it's gonna be for no loss of coverage, and I mean it's gonna be here now, and no prefetch. So we are coming here inside the QValue store, and here, as I explained, we have to decide what is the best action for that state, right? And so we already know, okay, the action that the Pythia decided from this process is going to be a no prefetch. So this no prefetch reward is going to go inside the evaluation queue, and the same for loss coverage. They work pretty much at the same time. They're going to work the same. And finally, for the other, so for the inaccurate one, it's going to be happening when we are evicting the entry. So if you're evicting the entry and there is not yet a reward assigned to that entry, it means that there was no prefetch was not decided, or there was no request for that entry. So it means it was an inaccurate request. And also there, then we can assign the reward to that entry. Have I answered your question?
Yeah, definitely. Thank you very much.
Okay, no problem. Are there some other questions? Maybe I forgot to ask if there are some other questions that people didn't understand well.
Yeah, we have another question. Wait.
Yes.
Yeah, I have a question related to training, and how does Pythia handle context switches? Does it?
Okay, this is gonna be, yeah, we're gonna talk about this in the discussion about context switching. So yeah, we will, if you keep the question, or we will then, I mean, you can think of the solution as well, and then we can come up with it later with context switching. Okay.
Thank you.
Some other.
Hi, yes, I have one more question. So can you go to the reward slide, please?
The one where you list all the rewards? Yeah, this one?
Yes.
Okay.
Yeah, right. So let's say that I'm an adversary and I know this reward function. And now I write a program which has a memory access pattern which explicitly knows this reward function. So what I'm trying to say is that I force Pythia to continuously access a stream which knows this reward pattern. And since it's an online algorithm, it will now change its, like I can influence the state machine, right?
Yes.
I can influence its reward pattern. So it is possible that I can deny access memory. Basically, I can pollute my cache with a dynamic scheme if I know the reward function, or basically inundate the prefetcher.
So I think I'm not, so as far as I understand, basically, I'm not so sure I understood your question, but so if you keep giving the same pattern, right? Then depending also, like if you give the same pattern, then it will always like give I mean, we hope, but usually because it works like this, it should give always the right prediction, right?
Yeah, right. So let's say that I pick the reward which has, let's say that I pick a pattern which has the highest reward value, and I keep issuing those requests for, let's say, 1 million instructions. Now Pythia will think that, okay, this is the maximum reward function that I'm going to get, and this is how this program is behaving. And then some other application comes in and it has a completely different pattern. But now my algorithm has become so tuned to seeing these high reward values that basically it just cannot recognize other patterns.
Okay, so
it's like getting those cocaine hits again and again, right? Your dopamine receptors are now completely overwhelmed, so you don't get any happiness in anything else. I don't know if that makes it clear.
No, I understand what you mean now. I understand. So this is also a bit related to like context switching, but not exactly. But the thing is that, so how I think is going to be solved is, first of all, the evaluation queue is only so it's only going to be 256 rows. But the problem here might be actually how the values inside the Q store are saved. And this is actually a good point that I didn't think of. If you always keep giving, like, if you always have the same access pattern, then it's giving always a good, like, always the same prediction, right? And it's gonna, like, I think it will take some time before, but it's always online. So it's gonna adapt. At one point, it's gonna adapt again its behavior to change to the next program that you're giving. But it's gonna take some time. So this is also, I think, related a bit to the training, right? So the training is that you don't know, actually. You don't know and nothing yet. So you need to take some time. And here in the same situation, it's kind of like you have to start from zero, because all the values in the Q store are messed up. And you have to wait before it gets tuned to the new program, to the new application that you are submitting to this queue. So yeah, it's actually a good point, right?
Thank you.
Some other points? Wait, I will need to go down again to the strengths, weaknesses, discussion. So if you have some idea for this, I mean, actually, I'm gonna give it right now, because the problem with, like, if it's a single core, it's a bit difficult, right? You cannot base your what you're doing on anything that you already seen before, because you're just starting fresh. So what you might try to do on a single core is actually try to use different initialization values. Maybe you have seen that usually for that state and action, it kind of converges to that value. So you try to initialize a bit better. It's similar to actually what you're also doing for machine learning in other situations. You try to have a good initialization, right? You try different initializations, and this might help to converge faster to the solution. So this is on the single core. But on the multiple core, Do you have some ideas how you can kind of facilitate this training problem? So I will give my solution, and then you can also give a points if you think. Yeah.
Yeah, I have a question on that.
Tell me.
So, is the system for all cores at once, or is it per core?
So the way that it was implemented inside the paper, it's each core has its own kind of Pythia version.
Okay.
So this is also a good point, because what I was gonna say is basically in this situation we have each core has its own, but let's say that we want to share it, right? Then there are some other problems. So what I was thinking first, that maybe a core is already the Pythia inside a core is already trained, and it will be maybe interesting to try and pass all the values from that core, from that Pythia version in its QV store, and pass it to the other cores, right? So they don't have this training time problem. Or you can have maybe one shared QV store between all the cores, but then this might bring other problems, because you have a lot of data that is coming in and out of the cores, and you have to find a place on the chip to place this QV store. I don't know very well about like this type of problems, but I think it's gonna also create some other types of problems with having just one shared structure. Maybe you have to decide like who goes first, who updates first, right? It's gonna be a bit problematic. And then, as we were also saying before, how do you manage context switching? And if you have some ideas here. I will briefly explain. So a possible idea that I came up with context switching is actually to kind of play a bit with the hash function, and you try to split the evaluation queue and the QV store. So for each thread, it's gonna have its own its own part in the store and the evaluation queue. But this brings other problems, right? Let's say, like, how do we do if you have like 50 threads? Then it's gonna be impossible, right? So this is a bit problematic. The other possible solution is actually, is it that bad that they share, different applications share the same information inside the QV store, so they use the same one? This was not actually tested in the paper, but it might be that actually all applications tend to converge to the same Q values. I don't know if it's the case, but it might be the case, or maybe they have similar values, like they converge to similar values. So it might be not actually a bad idea to just leave it like it is. Just let them kind of work together and figure out what is the best solution by themselves, so having them shared. Do you want to add something? Otherwise, I can go to the next discussion point. Okay, so the next discussion point is actually applicability. So
just quickly.
Yes.
Note on the multi-core training time thing.
Mm-hmm.
Why do we even care? Because presumably we are booting up a system, and if we're booting up an operating system, then there's already probably enough to do during startup. We would get through, how many cycles did you say they trained for?
So for the single core, I think it was 50, and for the multi is 100 million.
Yeah, we would probably get 100 million cycles in during system startup, right? So there should already be, the training should already be done for all cores when the productive work begins.
The thing is that, yes, that is partially true, but the thing is, I'm not so sure how they did it in the paper. They just wrote million instructions, but you have to consider that to train it, you actually need memory requests, not just any action, right? Not just any instruction, sorry, but you need actually memory requests to train it. So I don't know very well how what happens when you boot up the system, if it's gonna have a lot of memory requests at the start or not. And also when you're booting it up, usually you're running maybe the same application. So also that might be also another problem, right? If you're running the same application and then you need to run something else, maybe it's already trained on the wrong batch or the wrong data. So anyway, it's also a valid point, right? It's gonna what's gonna happen? Maybe 100 million is not so much. It's gonna be over in like 10 seconds from when you started your system. But I honestly cannot answer to this question exactly because it was not tested. But it's gonna be an interesting point to be tested, right?
Yeah, I also think that's probably because different applications have different memory access characteristics, and so I think it's probably best to tune it for each application. Otherwise, we could just don't use or have it like trained beforehand and then hard coded into the system.
Yes,
so we don't have to have the training itself if it's possible to have just a general system. Perhaps to the context switching, I would as my first thought would be to have the stores be switched into memory on context switching. So the operating system provides a memory address, and then the CPU has to write that in. But that's also going to take some amount of time. So
yes. Yeah, it's also it's gonna, you need to see a bit how long is it gonna take. Is it gonna be worth it, right? So, but it's a good idea as well, I think.
So in the paper they didn't look at context switching.
No, they didn't. They were just trying different workloads and see how it performs on those workloads. And they also, like, before starting to analyze it, they pre-trained it as well.
Okay. Yeah.
So then I'm gonna go to the there's some other points. I think I can go forward. So the applicability. So
I think
yes.
Before going forward, I want to make one point clear.
Yes.
So I think so the key difference between so let's say a traditional deep neural network based supervised learning and reinforcement learning is that, and especially the form of reinforcement learning that we are using here, is that it literally does not take as much as time that DNN takes to train for. So for example, I just want to correct it once that so what Aurelio said, right? Maybe 50 million or 100 million instruction it would take just to train it, and then we can use those information that it has trained for. It's actually not that high also. So what I'm trying to make here is that, so unlike supervised learning where you have a specific offline training phase and an online inference phase, this type of algorithm literally trains online and inference is also online. And the form of reinforcement learning that we are using here is just a table-based approach, right? And with a very massive hash functions, like massively hashing and just to make sure everything is hashed properly. So it's literally very fast to learn. And let me give you another example. It's like the way we have evaluated this idea is that all the prefetchers, including us and every other competing prefetchers, they start from cold. Everybody is learning something, right? I mean, yes, every prefetcher is learning some type of patterns in the program accesses. So everybody actually starts from cold, including Pythia, and then everybody goes to the end of the simulation. And finally, at the end of the simulation, we want to, so we want to like evaluate the performance, how good this prefetcher is, right?
Okay.
So while it's running up, then it's already like giving a reasonable performance, and
yes. So that's the key point that I'm trying to make here, is that everybody starts from cold and everybody runs to the end of the simulation, right? And at the end of the simulation, we still see that Pythia is performing way better than the other prefetchers. So we can safely infer that even with a cold start, Pythia's training is no longer than what other prefetchers are also taking to train, right? So that's the key idea that I'm trying to give here, is that Pythia's training time is not any much longer than the other prefetchers, like non-ML based prefetchers that we are even considering in this case. Did you get what I'm trying to say?
Aren't conventional prefetchers more like on for example, if you have a loop or something that they can figure out, okay, you now have contiguous memory access versus. Also, aren't they operating?
Just give me 1 second. I mean, maybe I just need to plug this. Aurelio, you can continue. Yes. You can continue.
Okay.
I'll come back to you.
Okay. So the second part of the reinforcement learning, actually, the way it's also implemented here, I think it's also, I think it has also other application. But so, what, in your opinions, where could you use this as well obviously inside computer architecture? So then maybe also I will speak, and maybe you came up with some others ideas as well. So my first idea was branch prediction, actually. So yeah, you based on you have the state, right? And then you can decide, okay, based on that state, what is gonna be the branch that you can predict. Now, another example that it came up with was actually switch between different energy modes. So this is actually done in the on the Apple chip for the MacBook. I think the chip is called M1X, and there they have kind of two modes, right, from between low power mode and performance mode. And you can also here use, based on the state that you have inside your computer, you can try to kind of predict and like decide what is the best energy mode that you can be in, right? If you're not doing anything very intensive, like from GPU to I don't know, from CPU, then you can also just save battery and go on the low power mode. And then I also was thinking of this solution, but actually I've seen that they also already implement some part. So adaptive, if you know what adaptive bit rate streaming is, basically you're trying, based on what is the network bandwidth, you're trying to predict, okay, this part of the, for example, we are talking about videos in this case, I'm gonna download it at this bit rate. This kind of also here, it's really works well with the reinforcement learning. You can kind of adapt it. Maybe I have also some others idea for this. Otherwise, I will keep going for the last discussion point, which is gonna be other machine learning methods. So there were also they already tried to implement some other machine learning methods, but what do you think? What will be the other, like some other machine learning method that you could use for this not a branch prediction, for this prefetching problem? I think it was also mentioned before, but basically it was, yeah. So neural networks, I think I supervise learning for neural networks. I try to come up also maybe to adapt it to some other machine learning problems, such as like k-nearest neighbors or Bayes or some other regression, but I think it doesn't work well with those other algorithms. But then the question is, how can you kind of transform Pythia such as that is becomes a neural network, like kind of transform the problem, but keeping similar to Pythia. So what I was thinking is actually kind of having the standard hidden layer, and then plus adding a softmax layer at the end. So you have the softmax that is gonna give you the best action in the end for the last layer, and then you're having the state at the end, the input layer, and then at the end you have all the actions. So you're gonna use the softmax layer for the last one, and then here you have to always kind of like play around a bit with the hidden layer, see how many nodes you wanna use, and how exactly you want to implement it. And another problem that I was thinking when you're doing a neural network, it might be that the input data is not so easy to like kind of create it, because like in some situation, like maybe no prefetch was actually the best choice, but you don't really know it for sure. And when you like, if you decide always to prefetch, you might run into some kind of over how do you call it, like overestimation. No, not overestimation, but yeah, you make it too similar to the real function, so it doesn't generalize well to the other function. I don't remember the word for that, but yeah. If you have some other idea for this machine learning, I don't know if how many of you did already machine learning course. Maybe you're not very familiar already, but yeah. And otherwise, if you have some other discussion points, I will leave a couple of seconds. Otherwise, I am finished with the presentation. Also, if you have some other questions or things that you didn't understand well, you can also ask right now before I finish the presentation. Okay, I think everything is clear. So I end the present. Maybe for the professor, if professor or some other assistants have some input, then also.
Maybe I would like to continue the discussion, because sorry, I had to stop because of the charge issue. Maybe these things are not adaptable enough, let's say. But yeah, so what I was saying is the following, that so yeah, as you said, this technique that we are applying here, the RL technique, it's not as heavy weight in terms of getting trained as you mentioned, right? So it's not that heavyweight for sure, right? And to satisfy, or let's say to support this statement, what I was saying, I would continue on the same line, that we evaluate this prefetching proposal along with all other prefetching proposals in the same way, right? So everybody actually starts from cold, right? You have zero idea. All other prefetchers had zero idea. So you can think of this zero initialization at a situation that, okay, your context has been switched. So that's a way we are also simulating, right? So you're starting from scratch. You have zero knowledge of the previous workload, correct? So literally you are not transcending any information from previous training, and you are starting from scratch. Everybody's starting from scratch, not just us. And then and we are evaluating in a way that, okay, 500 million instructions. After 500 million instructions, how much everybody else is performing and how much we are performing, right? So in the end, we see that Pythia is outperforming as he showed, right? 3%, 17%, whatnot. So we can safely say that even with the same methodology of evaluating other prefetches along with our prefetches, right? So if everybody starts from like full cold situation, still you would end up having a good performance. So that means even if, first of all, we can safely argue that Pythia's training time is as comparable as the others training time, right? And this also gives you that confidence that even if, let's say, context switch happens, or let's say some workload was basically, like as Aditya was mentioning, like some workloads was kind of bombarding, and then it got switched out, and then somebody else got switched into the same core. It can quickly start picking up from the new like workload, like what are the demands from the new workload. Yes, it would probably make some mispredictions in the beginning, because it has trained from the prior workload so much that it would take some time to at least get rid of that information, right? But then it can quickly pick up from where it's starting from. Okay, I mean, I can safely say that it would like pick up no later than the other prefetchers also.
Okay.
I hope that's clear. Make sense? Yeah. So yeah, I mean, that's from my side.
Okay. Some other from someone else, or?
Maybe if there are no more comments, I will make some quick comments. First of all, I think this is a work that's really important in an area that we need to do more research on. Basically, how do we enable techniques that can self-optimize themselves as opposed to humans designing the policies, because humans cannot really think about many dimensions when they actually design mechanisms and policies, right? Like this prefetching mechanisms, for example. And this work is a step in the right direction to make things much more learning, fundamentally more intelligent, let's say, in the core of the hardware. So I think it's good to look into a space like this. For example, in the past incarnations of the seminar, we talked about self-optimizing memory controllers, which is a work that we published in ISCA 2008, which is along the same lines. How do you design a memory controller based on reinforcement learning principles? So this sort of data-driven controller design is very important going forward. Because if you want to make fundamentally better decisions, I think we need to adapt. We need to be adaptable in the decisions. And what this work enables is that adaptability, I think. The second comment I will make is it's not easy to evaluate this sort of work also, because you need to look at many workloads to show the real benefits. And I think the paper does a good job, but it's also limited in terms of what it can do in a given space requirement. So I think the potential benefits of this work are not really fully, completely evaluated in the paper as well, right? There's some part of the paper that looks at performance on unseen workloads, for example. And I think that's really important. Basically, you've never seen these workloads, and you still do perform much better than prior prefetchers on those workloads, right? I think the third thing, I think Rahul made the correction in terms of training time, and I agree with that. I think one advantage of reinforcement learning is you can make decisions while you're learning. So there's no real distinction in a sense between training and making decisions, because you're making decisions while you're training. So this is very different from supervised learning mechanisms like neural networks, where you have an offline, usually offline training phase, where you train for a really long time with a lot of data. And in some of the deep neural networks today, it takes like days to train networks, right? You throw a lot of data so that you can figure out how to configure the connections in the neural network and the weights, etc. And then you have an online inference phase that doesn't exist in the implementation of, in the algorithm and implementation of the reinforcement learning. Fundamentally, reinforcement learning is really everything is online, right? Of course, you can use reinforcement learning to do offline training, but that's not what this paper does. In this paper, everything is online. And I think as Rahul mentioned, that's one benefit, certainly. That's one reason why reinforcement learning is quite applicable to this problem. The other reason is reinforcement learning fits the problem better, as it's mentioned in the paper, right? Because you have a lot of environmental effects. Basically, this is not a, let's say, this is not a classification problem that neural networks are very good at, because you don't know the right or wrong decision. And right or wrong decision, if you know it, depends on the memory bandwidth usage, for example. Basically, whenever you make a decision for prefetching, you don't get feedback sometimes, right? Because the processor may use it hundreds of thousands of cycles later, potentially, right? Even if you prefetch something accurately. So training is very fundamentally different compared to supervised learning. So I think I like your thinking that you want to apply machine learning to other
like reinforcement learning in this case. Yes.
To other reinforcement learning to other mechanisms. But I'm not sure if your last point on applying supervised learning works well.
So I think in the paper they actually mentioned it at the start. They were saying that I might be wrong, but I think it was like they also tried some neural networks and they were actually performing really well. But the problem is still this memory and the latency overheads that are really bad if you're actually trying to make it in the real world. So that was the main problem with that.
Yeah, maybe Rahul can answer that better.
Yes.
Rahul.
Yeah, I think there are previous works which uses like a traditional concept of supervised learning, right? Let's say LSTM, which is traditionally used for language modeling. So the key idea here is that if a LSTM based model can understand the correlation between the words, and it can predict what, like given a set of word, it can predict what would be the next word. So then this might also be helpful in this case, right? That given a set of addresses that you have seen before, you can literally predict what it's going to be the next. But then as we also argue in the paper, it's like, so first of all, finding what is the correct prediction is actually hard in case of prefetching. Like as Professor Mutlu was mentioning, like you might not even get the feedback, and that feedback might come like way later in the time that it was actually predicted. So it's sometimes it's actually hard to understand what's even a correct prediction. And more often than not, as we also show in the paper, that not it's not necessarily true that all correct predictions are actually useful for, let's say, performance, right? I mean, it might be also the case that you are making accurate decisions, but it's just stalling the demand request. So that's why it's just like underperforming, right? So I guess the crux of the problem lies in the inability to mold this problem in the supervised learning space. Yes, there are solutions which models this thing as a supervised learning, and they have kind of evaluated it in isolation of the system performance, right? And if you just consider it to be a fully accuracy driven like evaluation, then yes, it might probably make sense. But then if you start doing it in a simulation based, right, and what's the end result, what's the end performance result, then it might not be actually as easy as it sounds. Like, not always accuracy is analogous to performance. So there comes the the approach. What we believe that it should be the one that you should actually consider all the other parameters, like there's a system level feedback and like cache pollution or maybe energy consumption, right? And then you should learn from all of them rather than just being let's say unidirectional problem, like just on the accuracy optimization, right? So I guess that's why we think that RL is a better fit for this problem rather than just a supervised learning approach.
Okay.
Yeah, that sounds good. I think, I mean, I don't want to take more time because we're already a bit late, but
yes,
maybe we'll get back to it after the second talk.
okay, I will be here anyway, so yes.
Okay, sounds good. Thanks.
Thank you.
Thanks, Aurelio and Rahul. I think if you are done, we should move to the next talk, but we will turn off the YouTube live streaming based on the presenter preferences.